This work presents a method to categorize marginally stable thermoacoustic modes into acoustic modes and ITA modes based on phasor diagrams. All thermoacoustic modes in an echoic chamber is a result of the coupling between two feedback mechanisms. One is the acoustic feedback mechanism, which is the feedback between the acoustic source and the reflective boundaries. The other type of feedback mechanism which is discovered recently is the intrinsic feedback mechanism, which generates ITA modes. Here, the acoustic wave is generated from the acoustic heat source, the heat source, which is also an acoustic source, which travels upstream. This acoustic wave will perturb the upstream velocity, which in turn perturbs the heat release. This closed feedback loop will generate ITA modes. If we alter the flame parameters, for instance, we'll get a spectrum of thermoacoustic modes, such as this one. All dots in this thermoacoustic spectrum, it corresponds to a thermoacoustic modes with the aforementioned coupling. To limit our discussions, we will just discuss the modes on these snippets here, which corresponds to modes with marginal stability. Our aim in this work is to differentiate these modes into either acoustic modes or ITA modes. We want to know if those modes is about the mode shape, if we can find a characteristic mode shape for ITA modes, or we want to see if there is a specific flame parameter that can describe the ITA modes. Specifically, we want to know if there is a boundary between acoustic and ITA modes. First of all, I will introduce our tool, phasor diagrams. A phasor diagram breaks down a complex valued phase vector into its amplitude and relative phase at any time instance. For instance, if we are given an oscillating variable p, which is a cosine function, we can represent it in a complex plane. And this is the phasor diagram. We can see that this variable p is represented by an amplitude and a relative phase, and the rotation of this vector just represent the time periodicity t. However, what is important for us is just the amplitude and relative phase, and the time dependency is generally factored out. Phasors is not a new concept. It has been used in other fields to represent signals and wave superposition and propagation. For instance, here I'm showing an RLC circuit. Here the phasors is used to represent the component voltage, and the length is the magnitude. The angle between different phases to the horizontal line is the relative phase between the voltage and the current. By doing simple vector addition, we can calculate the net voltage in an RLC circuit. In this work, we will apply the phasors analysis to acoustic waves propagation. First, let's look at this ideally closed open channel. We have chosen the reference position to be the inlet. At the inlet, the reflection coefficient is equals to 1, therefore F and G are equals. They are in phase as shown in this phasor diagram. Across the channel, the acoustic wave propagates according to this function. This just means that the F and G phasors will rotate clockwise and anti-clockwise. This rotation will continue until it reaches the outlet. At the outlet, due to the reflection coefficient being -1, the F and G phasors are anti-aligned from each other. We can stack these two-dimensional phasor diagrams together in the spatial direction to obtain this three-dimensional phasors diagram. In this diagram, we can see that the eigenfrequency is related to the total phase rotated by the F and G phasors. Here we can see that we can obtain the classical 3/4 wave eigenfrequency by solving the phase covered by the FNG phasors. We can also generate the primitive variables pressure and velocity fluctuations by doing simple summation and subtraction of the two FNG phasors. Here we can see that we have performed the superposition or vector addition of the FNG phasors. By doing so, we will also generate the phasor diagrams for the primitive variables P and U. In this diagram, it is clear that we have obtained the classical mode shape, standing wave mode shape for the pressure and velocity. So, in a short conclusion, we have shown that phasors can represent the acoustic wave propagation in space by rotating the FNG phasors. We can also obtain the system eigenfrequencies, which is congruent to the phase coverage. Finally, we can also obtain the primitive variables by vector addition and subtraction of the FNG phasors. Now let's introduce a passive flame to the system, which is just a simple temperature jump. A temperature jump introduces a jump in acoustic impedances in the system, which also changes the speed of sound in the upstream and in the downstream. One naive approach to determine the eigenfrequency is to generalize the quarter wave mode equation. This is the quarter wave mode equation that I've shown previously in the previous slides. Here we can see that the travel times from the inlet to the outlet is taken into account. To generalize this equation, one might just think that the total travel times is just the summation of the upstream travel times plus the downstream travel times. However, this equation is not valid because it ignores the mass and momentum conservation. Instead, we will use the phasor analysis to calculate or to determine the eigenfrequency. At the inlet, we can recover the aligned phase of the FNG phasors again. Throughout the cavity, the FNG phasors rotate clockwise and counterclockwise. Across the flame, since we want to use the Rankine-Hugoniot jump equation, we will decompose the FNG phasors into the primitive variables P and U. The Rankine-Hugoniot equations coupling relations takes into account the mass and momentum conservation, which is shown here. The pressure is obtained, the downstream pressure and downstream velocity is obtained. We can reconstruct the FNG phasors using the pressure and velocity information, and those phasors will continue their rotation until they reach their anti-aligned formation at the outlet. Due to the temperature jump, we can see that there is an artificial phase advance across the flame. We can see this again in this two-dimensional phasor diagram. This artificial acceleration of the phasors, FNG phasors, caused the total phase coverage by the FNG phasors to not be 3.5 pi. Instead, it is less than that. Therefore, the eigenfrequency is also less than the 3/4 wave eigenfrequencies. Now I will introduce an active flame into the system, which is a flame with an unsteady heat release component. The active flame doesn't only affect the pressure, but also affects the velocity downstream. In this diagram, we can see that the Rankine-Hugoniot equations dictates that the downstream velocity is a summation of the upstream velocity and the heat release contributions. The heat release contribution is described by this term, which is the flame transfer function multiplied with the upstream velocity. For an arbitrary flame transfer function phase, we could either have a stable or an unstable system. Here, the Rankine, the Rayleigh index describes this phenomenon by looking at the phase between the pressure and the heat release component. Here, our system, in our system, the pressure and the heat release component has a phase that is less than 90 degrees, therefore this example here is unstable. To limit our discussions for marginally stable modes, the FTF phase must be a multiple of pi. There are two situations. First, the FTF phase is an odd multiple of pi. Second, the FTF phase is an even multiple of pi. For these two situations, the FTF could be negative or positive. If the FTF is negative, the heat release contribution acts against the velocity. Therefore, the artificial phase advance across the flame increases. As a result, the total phase covered by the F and G phasors decreases, and therefore also the eigenfrequency. The opposite is true. By looking at this, we can say for each gain value of the FTF, we can obtain a unique eigenfrequency. This is shown in this diagram. For any values of FTF, there is multiple value of eigenfrequency, unique eigenfrequency. We can see our 3/4 wave eigenfrequency here for the passive system. If we increase the gain in the even pi region, where the FTF is positive, the eigenfrequency increases, as predicted. In the other direction, the eigenfrequency decreases, as predicted. We have noticed an interesting property when we decreases the eigenfrequency in the odd pi region. A velocity flip across the flame is observed. First, we will start with a weak flame. With a weak flame, the downstream velocity and the upstream velocity are still in phase. When we increase the gain, the heat release component compensates the upstream velocity such that the downstream velocity equals to 0. Further increasing the gain, the heat release contribution will overcompensate the velocity so that the downstream velocity is 180 degrees out of phase from the upstream velocity. This is an interesting property because we can also observe this in a pure eta modes. In a pure eta modes, the velocity must flip by pi radians across the flame due to the anechoic boundaries. The F phasors in the upstream must always be 0 due to the reflection coefficient being 0. Therefore, the pressure must always be the negative of the velocity. At the flame downstream, the reflection coefficient equals to 0 dictates that the pressure must always equals to the velocity. Due to the change in velocity sign, the velocity must flip across the flame. This is similar to what we have observed in a thermoacoustic modes with sufficiently high gain in the odd pi region. Therefore, we can say any thermoacoustic modes with a velocity flip across the flame is an eta modes. We can shade out a region in this diagram which shows that any modes in this region is an eta mode. We can also assign a trend in the pressure gradient to define the eta mode. The linearized Euler equations give a coupling relations between the velocity and the pressure gradient. If Since an eta mode means a change in sign of the velocity, this also means that the pressure gradients must change in sign. We can look at these two examples. On the left-hand side, this is an eta mode, and on the right-hand side, it is an acoustic mode. In an eta mode, the pressure gradient changes in sign across the flame. We can see that in the upstream, the pressure has a negative gradient, and in the downstream, the pressure has a positive gradient. In an acoustic mode, the pressure doesn't change in sign. Both the pressure gradient in the upstream and in the downstream have a negative gradient. Now we'll look at several phasor diagrams for different types of thermoacoustic modes. The first one is an acoustic mode. We can see that the velocity are in phase. And then we'll look at the transition mode where the downstream velocity diminishes. Next is an eta mode. The velocity flips by 180 degrees. Then we recover the three-quarter wave modes that we are familiar with. Finally, we'll compare the range of eta frequencies that we have predicted in this work with the other methods proposed in other works. We can see that the frequency range roughly agrees with the other methods. In this work, we have demonstrated that using phasors that the eigenfrequency of the system is related to the total phase covered by rotation of the F and G phasors. We have also shown that a flame will introduce a phase advance across the flame, which then modifies the eigenfrequency. Finally, we can distinguish eta modes from acoustic modes by looking at the flipping of the velocity across the flame. If there is a flipping of velocity across the flame, we are looking at an eta mode.